Hello, Math 120, and this is Professor Gonzalez, and I'd like to take a look at some homework problems from section 4.6, which is looking at special products and factoring binomials, and 4.7, which is just more practice factoring. So we've done factoring in 4.4, 4.5, and getting more specific, but just practicing more basically. And remember, I said, when you take a look at the book is showing that you can factor using grouping. There is a trial and error method. And if you go online, there are, probably 10, 20 different ways of factoring. And I really don't care which way you use. Just want to have a good, consistent way. Now I'm going to show grouping because the book showed grouping, and also grouping, in my opinion, is a way that almost everybody really can pick up. The negative is that it's a little bit long and it takes multiple steps. So I'm going to start with that because I think it's the most attainable. And then if you start finding faster ways like the AC method that I showed, or trial and error, guess and check, if you're getting good at that, those ways can be really fast and nice. Also will show some of these formulas, special formulas that make it faster if you can recognize them. That happens in this 4.6. Okay, so let's start off. I think we're going to start off by taking a look at some of these special formulas here, special factoring formulas. So I'm going to start right here. And let's just take a look and see what happens when you have a perfect square. Let's start with that. Let's say like x plus, let's say 5, quantity squared. Well, we know that means x plus 5 times x plus 5, right? And I know we already talked about this in one of the chapters when we were talking about multiplying these perfect squares. But now we're on the other side of it. Instead of multiplying, we're trying to factor them. But in order to factor them, knowing how they multiply is part of it. So we multiply x times x, we get x squared. X times 5, we get 5x. And remember, with these types of perfect square binomials, the two middle terms will always be the same. So we have this real pattern that happens here, right? That's double. Those are double. So what we start seeing here is that, now let me go like this. Let's add that together so we get 10x plus 25. So now what we want to do, instead of multiplying it, we want to factor. So we're posed with this problem right here, x squared plus 10x plus 25. Now, by the way, you might say, isn't that an easy factoring problem, and can't I just do this with it, right? And that is totally true. It multiplies to 25 and adds to 10. But that's not really the point of 4.6. 4.6 is trying to look at shortcuts that make it faster. And when the problems get more difficult, these shortcuts can really come in handy because maybe looking for what multiplies to the c value and adds to the b value might be difficult because the numbers might be quite large. And so let's just get the pattern right now. So what this is basically saying is if you see a trinomial that fits this pattern, the a is squared, the b is squared, and the middle term is a times b, and that gets doubled. If you have that pattern, then it will always factor down to this nice a plus b quantity squared. So really what it's about here on this step right here is trying to identify, is this a perfect square trinomial? And so for me, what I do, I think I'll use a little color here. So let's make our a red. So first things first is identify the a. And that question is this a perfect square? Yeah, x squared is a perfect square. Is this last term a perfect square? And the answer is yes. 25 is a perfect square, 5 squared. Now the question is this middle term, as this said, is this middle term double a times b? What was a again? A is this x. And what is b? B happens to be this blue 5. And when I take 2 times x times 5, I get 10x, which is exactly what this middle term is. So therefore, my a value is that x, my a value is the x, as you can see right there, and my b value is the 5, as you can see right there. And, of course, I'd explain it and show the formulas and stuff, but if you don't have to go through all the explanation like I did, you can actually factor these really quick, especially when the numbers get large. This one's not going to be that punishing if you went ahead and just looked for two numbers that multiply to 25 and add to 10, because it's just 5 times 5 and 5 plus 5. So that wouldn't have been that difficult. But when the problems get hard, this really does save a lot of time. So there's one of them right there. Okay. There's another perfect square trinomial that also works. And it's almost the same. Let's see, maybe we should put a highlighter box around this as one of our formulas. The other one that looks very much like this is just a squared minus 2ab plus b squared. Notice the only difference is this minus sign instead of the plus. And what that changes is it changes that our perfect square is a difference a minus b quantity squared. We'll put a little highlighter box around that as another special formula that helps us identify the a's and b's. And once you identify your a and b, you factor down quickly. Of course, multiplying it up is another way of checking it, right? And if I take x plus 5 squared, that was up here, and you see I multiplied it and got the x squared plus 10x plus 25. So you could always multiply and see if you factored it correctly. Okay, so another thing we have is we have three binomials. Actually, let's just start with these two. Let me give you one more, and then I'll go to the let's start with those two. Let me go with one more actually. And so this is another one called a difference of two squares. So these are difference of two perfect squares, and if you've ever multiplied x plus, let's say, 4 times x minus 4, whenever you multiply those, if you've done a bunch of those, you'll start realizing pretty quick x times negative 4 is negative 4x, 4 times x is positive 4x, and every time, and then 4 times negative 4 is negative 16. Every time we do these problems that have this format, we get a 0 in the middle, and so we end up with a binomial x squared minus 16. So that is another common pattern that comes up a lot. And what I want to show, okay, so once again, we just multiplied here, but what would our problem look like? Our problem would look like this: x squared minus 16, and we want to factor, and we want to get it back to that. So this is called a difference of two squares. Do you see the difference? We have, so the key part, let's see, how did I do it up there? Okay, yeah. So let me put a formula right here. If you could identify this binomial, right? This binomial means it has two terms, as a perfect square minus a perfect square. If you could identify that, we can be sure that that will factor down to a plus b times a minus b. And so by knowing this pattern or formula, we can save ourselves a lot of time. So it's really important when you look at this, you say, okay, it's a binomial. The question is this a difference of two perfect squares? So is x squared a perfect square? Of course it is. Let's make it red. X squared is x squared. And let's make this blue. Is 16 a perfect squared? And yes, it is. 4 squared is 16. So now you've identified the b as blue, and you've identified the a as the red. And so when you come through and use our little nice formula here, you just replace all the little pieces and parts. We know that x is our a value, so we know that this problem up here will factor down to x plus the b, which is 4. Whoops. Factors down to x plus 4 times the quantity x minus 4. And that saves a ton of our time as well. So let me go ahead and put a little highlight around that formula. So those are 3 that come up a lot. The next 2, which I'll do towards the end of this lesson, don't come up quite as much. But these 3 come up very often and can save ourselves a lot of time. So let's go ahead and go back to the beginning of this whole thing and see if we can do these problems. Now, if you identify this as a perfect square trinomial, that would be awesome. But since the numbers are so small, you might have actually just said, so look at this. I just want to show you, this is a perfect square trinomial, and I know it is because this is a perfect square. This is a perfect square, right? 3 squared is 9. In the middle is 2 times the x times the 3, right? 2 times negative 2 times 3 is negative 6, and then we have the x. So it fits that perfect square trinomial. So then you would know that it would just break down to x, right? X, and then since there's a minus sign, it's x minus 3 perfect square, and you'd be done. Okay, now this problem is the numbers are so small that it's very likely that the pattern, using the pattern is almost slower in some cases. So it wouldn't be a big penalty in this one if you said, well, I think this is an easy problem. Look at that. That's an easy problem because it has a 1 right there. So I'm going to look to see what multiplies to 9 and adds to negative 6. And you would say, well, negative 3 times negative 3 gives me a positive 9, and negative 3 and negative 3 adds to negative 6. So the answer is x minus 3 times x minus 3, which is just x minus 3 squared. Okay, and so both ways were actually pretty quick. Now the next one, they're actually giving you a clue. They're trying to tell you, factor the following perfect square trinomial completely. They didn't tell us to use a perfect square trinomial up here. They just said factor. But it was a perfect square, so you could have. Now this one, if you don't use the formula, the problem is going to get much harder, because look at the last problem. It had a 1, so it was an easier problem. Well, this has a 4, and it's not a greatest common factor, so you can't factor it out. So if you're going to do it the old-fashioned way, which you could, you'd say 4 times 25 is 100. What multiplies to 100 and adds to 20. So that's something that could be done. But the bigger these numbers get, the nastier the numbers get, the harder this technique will be. And that's when a nice pattern really does help out a lot. Okay, so we're going to use the pattern because that's what we're practicing right now. So here's the problem. It says 4x squared. Let's see, I'm going to run out of space. So I think what I want to do is just erase a little bit of this stuff just to give me a little more space to work here. That was a negative 6. Okay, so the problem happened to be what? 4x squared plus 20xy plus 25y squared. So what you want to start getting used to is when you see a perfect square. So the very first thing when you're factoring problems, the very first thing, if you can, is there a common factor to factor out? And the answer is not on this one, so you can't do it. That's the first question you should ask, because if there's a common factor, it'll make numbers smaller and factor in terms easier to deal with. But there isn't any. The next thing I'm starting to start to highlight for me is I'm seeing a perfect square. So then you want to write it. So do you see a perfect square here? Do you see a perfect square here? That doesn't mean it's a perfect square trinomial, but it's at least possible, right? So 4x squared, write it as a perfect square. That's 2x raised to the second power. So 2x times 2x is 4x squared. Now what about the last term over there? Can you write that as a perfect square, 25y squared? And yes, 5y times 5y is 25y squared. So far it is fitting the model. Now, the final piece to fit the model is the middle term has to be double what? It has to be double the red a value, which is 2x, times the blue b value, which is 5y. So the big question is, does it follow the model? We know this is a perfect square and this is a perfect square. The middle is 2 times 2 times 5, which is 4 times 5, which is 20xy, and that's exactly what we have in the middle. Therefore, we have a perfect square trinomial. And now we know all we have to do is write the answer. It will be factored. So the a value we figured out, a value is 2x. We figured out the b value already. The b value is just 5y. And make sure you have the right sign. How do you know what sign is? Well, it's going to be a positive if this is plus. If this is negative, then it's going to be a negative, okay? That's how you can tell. Let me get rid of that. And it's a positive, so this is a plus. And you're done. 2x plus 5y quantity squared. Let's try another one. Okay, so on this one, I think what I'm going to do is, well, always, first thing you should do is, can you factor out the greatest common factor to make the numbers smaller and easier to work with? Can you? And I think there's probably a common 3, and you can use your calculator. And can you factor out a 3 on each one of these? That's kind of what your brain is thinking. And the answer is yes, so we factor out a 3. And that's going to leave us, when we factor out a 3, a 16p to the 4th minus 24p squared plus 9. Okay, so now I'm seeing perfect squares, and that makes me start to wonder here. Can I write this as a perfect square? Can I write this as a perfect square? And can I write the middle as double that a times b plus 5? Okay, so there's a lot going on there, but very first, can I write that as a perfect square? Yes. 4p to the second times 4p to the second is 16p to the 4th. Next question, can I write this as a perfect square? Yes. 3 times 3 is 9. And is the middle term negative 2 times the a, which is 4p squared, times the b, which is 3? And we have to answer that question, and that will tell us it all. When we multiply that, we get negative 2 times 4 is negative 8. Negative 8 times 3 is negative 8 times 3 is negative 24, and then we have that p to the second. That's exactly what we have in the middle. This is a perfect square trinomial. So we factor it down to a perfect square. And we already identified the a value right there, 4p squared. And we also identified the b value, which is 3. And we also know the sign, because the sign is always going to match the sign of that second term. And I can see a mistake I'm about ready to make. It's a common mistake. And that common mistake is, let's make sure I don't erase that. That common mistake is to forget, after we factored out the 3, to forget that 3 in the final answer. So there should be a 3 right there. So the answer is 3 times the quantity 4p squared minus 3 quantity squared. Okay, and that problem would have been a bigger pain for sure, if you're going to factor traditionally by multiplying that 16 times 9, because that's a big number, and then what adds to negative 24, right? Okay, they're giving us a clue here. You factor by using a perfect square trinomial formula. Oh, okay, they're telling it to us. That doesn't, a lot of books don't tell you what strategy. They just say go for it. So that was nice of them. So let's see if we can identify this. First question is there a greatest common factor with this? What number are we on? Number 4. And 64, 80, there's common there, but 25 is 5 times 5. Nope. So no common because of that 25. So I'm just going to write this out and see if we could identify it. So we've got 64x squared minus 80x plus 25. Definitely has a lot of potential, right? If this is truly a perfect square, they told us it's a perfect square. But anyways, if you didn't know, we're trying to see, is that a perfect square? Is this last term a perfect square? If we get a no on one of those, it's not a perfect square trinomial, and then you have to factor by using multiplying a times c, right? And using that whole diamond thing, what multiplies to blah, 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 okay? But we're trying to see if this is a perfect square. So, okay. And then the final test is the middle term -2 times the a value times the b value? Okay, I'm going to use some color to highlight what's going on. 64, is that a perfect square? Yes, that is 8x times 8x gives me 64x squared. So that is definitely a perfect square. Is my last term 25 a perfect square? Yes. 5 times 5 is a perfect square. Now, is the middle term, the b, and if I do it in order, I'd say -2 times the a which is 8x, times the b, which is 5. And when I multiply that together, I better get my middle term. And if I don't, then it's not a perfect square trinomial. Well, I get -2 times 5 is -10 times 8 is -80, and we have an x, -80x. Definitely fulfills that whole idea that we have a middle term, and this is a perfect square trinomial. It will factor down to my a value, which is 8x. And let me look for my b value, which was just 5. And my sign, which was subtraction. So you should get an answer of 8x minus 5 quantity squared. Next problem. So the first thing that jumps out every single time, which you should be looking for, and if you don't see it on this, it's not going to be it's not a perfect square right now, because 2 is not a perfect square. But there is a common factor of 2 that can be factored out, so you need to do that. Otherwise, the only other way to do it is say 2 times 18 and then do it our traditional way and then group it and all that. But we're trying to see if there's some shortcuts and actually factor the perfect. They told us it's a perfect square, right? So the way to really see it is you have to factor out the common 2, which leaves w squared minus 6w plus 9. Now this particular perfect square trinomial is the numbers are so small and easy that actually it mirrors that first problem, right? It mirrors that first problem, really. I think it is the first problem. So you could have done it in a traditional way, but I just want to follow the formatting that we're doing here, and that is identifying perfect squares. So is that a perfect square? Is that a perfect square? Is this -2 times a times b? Is that confirming that we definitely have a perfect square trinomial? W squared, yeah, w times w is w squared. And 9, yeah, that's 3 times 3 is 9. So now is the middle term going to be -2 times w times 3? And when I multiply -2 times w times 3, I get -6w, which is exactly what we have in the middle. This is definitely, don't forget your 2. This is definitely a perfect square trinomial. The a value is w. The b value is 3. And we can identify our sign pretty quickly as subtraction. So you should get 2 times the quantity w minus 3 squared. Okay. Factor the perfect square trinomial. So once again, you can use the pattern here. What if you didn't see the pattern? Well, if you didn't see the pattern, then you would use our traditional way of doing it. This might screw you up a little bit, that fourth power. But by just multiplying and kind of seeing the multiplication process and trying to kind of reverse engineer as you're factoring, you can kind of figure out where that goes. But let's go ahead and just continue with our formula here. So we've got z to the fourth minus 4z to the second plus 4. And so the question is that a perfect square? Is that a perfect square? Is the middle 2 times my a times b. Is z to the fourth a perfect square? It is. Z squared times z squared is z to the fourth. Perfect square. Ding, satisfied. Okay, step 2. Is 4 a perfect square? Yes, 2 times 2 is 4. Ding, perfect square, satisfied. And finally, is the middle term going to be negative 2 times a, which is z squared, times b, which is 2. When I multiply that together, I get negative 2 times 2 is negative 4 z squared. And that's exactly what I have there. Ding, satisfied. Those 3 pieces are satisfied. This is definitely a perfect square trinomial. And I know my a value is z squared, and I know my b value is 2, and I know my sign, look, is minus. So the answer is z squared minus 2 quantity squared. Now we are changing it up. Factor the difference of 2 squares completely. Difference of 2 squares. Now remember my difference of 2 squares formula down here. It says if you have the difference of 2 squares, the difference of a perfect square minus a perfect square will always factor down to a plus b times quantity a minus b. These come up a lot, and they're really fast if you identify them. Once again, they could be done the slow way. Let me just show that real quick, then I'll erase it. The old-fashioned way, just so you know if you forget something, you still can do this, right? So look at it, it's x squared minus 36. To do it the old way, you'd have to remember that the middle term is 0 then, right? So the old-fashioned way would be, what two numbers multiply to negative 36 and add to 0? And you might go, nothing. Wait a minute, something does. How about negative 6 times 6 is negative 36, and negative 6 plus 6 is 0. So this would factor down to x, because it's an easy problem, right? It'd factor down to x minus 6 times x plus 6. And that is the answer, okay? So that does work. Now, we're all about trying to use our new formula, difference of 2 squares formula, and seeing this pattern, because when the problems get harder, the difference of square formula really comes in clutch, making it easy for us. We've got x squared minus 36. This is all about identifying it. Is this a perfect square minus a perfect square? So then we go through and we say, is x a perfect square? Yeah, x times x is x squared. And what about 36? Yes, 6 times 6 is 36. And is there a different sign in between, a minus, right? A difference, which is minus? Yes. So that means it's going to for sure have this format of a difference of 2 squares. One's going to be plus, the other one's going to be minus, and then we have x, and then we have blue 6. And if you multiplied that out, you'd find out that you would get exactly what we started with. So that tells you that you factored it correctly. Let's do the next one. The next one says 9z squared minus 25. So identify it. Is this a difference of 2 perfect squares? So is 9z squared a perfect square? Yes, it is. 3z times 3z is 9z squared. Also, is 25 a perfect square? Yes. 5 times 5 is 25. Is this a difference? Yes, it is a difference. So it's a difference of 2 perfect squares. It perfectly fits our model of a difference of 2 perfect squares. And so, of course, one's a plus, one's a minus. And so we take our a value, which is 3z, and we take our b value, which is 5, and we've got it factored perfectly. Okay, that's 8. Those are 8 problems. Let's move on down. There's my notes. Let's move on down to number 9. Factor the difference of 2 perfect squares. Ooh, this is where it's starting to get uglier. But if we have our formula to fall back on, it does help a lot. So let's write this out first in black. Starting problem is 64x squared minus 121y squared. So first of all, is this a difference of 2 perfect squares is the question. Is this a perfect square minus another perfect square? So question, Is 64 a perfect square? Yes. 8 and x squared is, so 8x times 8x is 64x squared. And second question, is 121y squared a perfect square? And yes, 11y times 11y is 121y squared. So it is a difference of two perfect squares. So just like that, we know that it will factor down to a plus b, a plus b, a minus b. So we go ahead and find our a. We already found our a. 8x, 8x. What's the b? You ask. It is 11y. And 11y. Got a little tight on space there, but anyways, the answer is factored down to 8x plus 11y times the quantity 8x minus 11y. Next problem, factor the difference of two perfect squares. Now when you look at this, zoom in a little bit, 20 is definitely not a perfect square, so something does not look right. So, but remember, every time you factor, the very first thing you should be doing is you should be factoring out the greatest common factor to start it off, because if you do that, the numbers get smaller, and in this case, the pattern reveals itself. So now let's see. This is 20p squared r minus 125b squared r. So what is common? Well, I think that there is a common 5 here, right? 5 goes into 20, 5 goes into 125. So let's try that. Let's factor out a 5. And it also looks like there's a common r. So let's factor out the common r. What do we have left now? So we factor out a 5r, we end up getting a 4p squared minus 125 divided by 5 is 25b squared, and then the r factored out. Now, don't forget the 5r. Now the question is this a perfect square minus another perfect square? So, how about 2p times 2p is 4p squared? That's true. And how about 5b times 5b is 25b squared? True. And we definitely see the difference of two perfect squares happening here. So we know that this will, for sure, and maybe I just leave it here because of space. So we've got the 5r, and it will for sure factor down to a plus b, a minus b. So let's fill in the a's and b's. A is 2p, and the b value is 5b. And there you go. You factored kind of a nasty difference of two squares problem. You had to factor out the greatest common factor first, which was 5r. Let's look at number 11. And number 11, it's just right. It's just a way of looking at things to see this one, and you're probably not expecting to see a binomial as a perfect square, and so your gut instinct is to multiply that out. But you're missing a nice little pattern that's happening here, because we always ask ourselves the question, is this a perfect square minus a perfect square? Well, this one is already written as a perfect square, right? It's already r plus f times r plus f. It's already a perfect square. And the b value is not revealed because it's not written as a perfect square, but we know 2 times 2 is 4. Now we've got the b. We got the a, we got the b. We're done. Okay, we are done. Well, we have to follow up and show what our answer is. But look at this. It's just going to be, and we got to be a little bit careful here, because it's going to be a plus b and a minus b. But what is the a? The a is that red r plus f, and the b is just 2. So there's your answer. R plus f plus 2 times quantity r plus f minus 2. And if there were any like terms, you'd actually have to add them together inside the parenthesis, but there are no like terms, so they are simplified completely just like that. Let's take a look at number 12. Number 12, now we have a new type of binomial that we need to factor. Now this one's kind of a pain, but it does come up. It doesn't come up as much as the three I just showed you. But I also want to kind of get you to mentally, let's take some notes right here. I want you to focus in on this idea of binomials. So when you're factoring binomials, what's a binomial? Well, it's like when you have two terms, right? Something like that, right? You separate it with addition or a minus sign. So you've got one term, a second term. When you're factoring binomials, okay, the only way you really can factor them is factor out the greatest common factor, number one. And then number two, go down the checklist. Go down the checklist. I really squished myself on the right-hand side of this page here. Don't have a lot of space, but go down the checklist. And what's the checklist? It's going to be one of the three following binomials that are factorable after you factor out the greatest common factor. And what are they? The first one, you already know. Difference of two squares. A squared minus b squared. What does that factor down if it's that? Factors down to, well, I don't have a lot of space. Let me just show you the three. So this is one of them. This is another one you're going to want to identify, which is a cubed minus b cubed, a difference of two cubes. And there's a third, a cubed, plus b cubed. That's it. There's just three special binomials. So after you first tried to factor out the greatest common factor, then the other thing is to check, is the binomial I'm not trying to factor one of those three special formulas, and if it's not, then it's prime, you're done. Okay, so that's a good strategy for when you're looking at binomials. So we've already looked at this formula, but we need to take a look at the next two. So this one's called a difference of two cubes. Okay, so difference of two cubes. I'm going to show you the formula. Maybe I'll do a problem. Let's see. Yeah, okay, let me show you the formula, and then I'll do a problem in reverse just so you can check it. Or let's just check one of our problems as we do up there. Okay, yeah, so let me just show you the formula. So when you see the difference of two perfect cubes, that's going to look like this. A cubed minus b cubed. The formula is a little bit of a pain. The formula is going to be a minus b times a trinomial, which is a, try to make that better, which is a squared plus ab plus b squared. Now that little guy gets messed up a lot because it looks so much like what? It looks so much like that guy right there that has a 2, right? So you got to be really careful when you're doing these perfect square trinomials, a squared plus 2ab plus b squared. But when you're doing a difference of two cubes or sum of two cubes, wherever that is at coming up, it's just ab. So you can see why someone would mess that up. Okay, and then the other one is called the difference, or no, it's called the sum of two cubes. Sum of two cubes is just going to be a cubed, you guessed it, plus b cubed. Now the difference is with the two formulas are the signs now. And when it's a sum, you start with a plus b. And then it's a squared minus ab plus b squared. So you could kind of see that some of the differences are here is that when it's a subtraction problem, you're going to start with subtraction, and then the signs alternate, minus, plus, and the last one's always plus. And then on the other one that is sum, right? You start with the sum, then you alternate plus, minus, and the last one's always plus. Okay, so that's how that is done. And I've had students that have told me their teacher had a little song for these things. So anyways, I don't know. I don't know these songs. So if you look them up, I'm sure they're online. But these are the formulas that really have to be memorized. We don't have a great way of factoring these cube ones other than memorizing them. We don't have the tools. Whereas with these other formulas that we have, these special products or special formulas, these guys over here, right, they're fast if you get proficient at them. But we do have other ways of factoring them by using traditional methods. But the cubes, no other way really. At least not in this stage of our math progression. So it's got to be memorized. Let's go ahead and see if we could implement these. And we're going to take our time. Where are we at? We're going to take our time. Where am I at? Right here. We're going to take our time, and then I think if we have space, we're going to go ahead and multiply it back so you can see how it, get a little more insight. So I'm going to start way up here. And so that's going to be starting with x cubed minus 27. The big question is this a perfect cube minus a perfect cube? Okay, that is the big question. So is x cubed a perfect cube? Yep. X times x times x is x cubed. That 3 is bugging me. There we go. And is 27 a perfect cube? Yes. 3 times 3 is 9 times 3 is 27. Yes, it's a perfect cube. So it's a difference of two perfect cubes. It will factor, I don't know if I'll say quickly, but pretty quickly, right? If you know the formula, down to the formula, which is going to be a minus b times the quantity a plus ab plus b squared. So let's see if we can figure this out. My a value is this red x. So x goes here, and x goes here. And it's almost harder for me to do it this way with the colors and pieces. X is going to go there. Okay, so I need to have an extra parenthesis. So what the formula is, I think I'm going to put the formula down below because that's a little annoying not having the formula right here. The formula is, when I'm teaching it at least, a minus b times a squared plus ab plus b squared. Now that I thought about this, okay, yeah, I could make this work. How do we get that out of there? Oh, go. I don't know. This every once in a while gets me. There we go. Okay, there's a button. Now I learned. Okay, so let's use the color on this one. So this x value is known as my a value, so that has to replace these pieces. And we did. And the thing you have to remember is this one gets squared. And we did that. Then we must replace our b values with 3. 3 is our b value. So 3 is going to go there, 3 is going to go there, 3 is going to go there. And once again, we have to make sure that we remember that that guy gets squared. So let's insert the 3's. 3 goes here, 3 goes here, and a 3 goes there. So with the final answer, I think I'm going to erase the formula now because it's kind of in my way, trying to do the final answer. The final answer, I guess I'll do that in black. It's just going to be x minus 3 times the quantity x squared plus x times 3 is just 3x plus 3 squared is 9. So that is your final answer. Okay, I wanted to multiply that out to check it. It's not going to leave me a lot of space to do this problem. So we have space down here, so I think it's a good idea to at least show this once, and I think I do have space at the bottom. Yeah, I do right there. So what just happened with that problem? We just had, was it the difference? Yes, it was the difference. So we just had this problem right here, x cubed minus 27, and that just factored down to an equal, right? X minus 3 times x squared plus 3x plus 9. That's what we just did on problem number 12. Now, how do you check it? You can check it by multiplying, right? And let me get rid of that because it's kind of in my way for the multiplication. We can check it by multiplying, and the multiplying in this is not fun at all. So this is the equal sign right here, right? So now we're going to multiply x times x squared is x cubed. X times 3x is 3x squared. X times 9 is 9x. Negative 3 times x squared is minus 3x squared. Negative 3 times 3x is minus 9x. And negative 3 times 9 is minus 27. And you might be saying, wait a minute. How is all of this mess going to end up looking like? How's all of this mess going to end up looking like this? Well, it's going to look like that because we have like terms that are not just like, they are opposite. So I have an opposite. I've got 3x squared and a negative 3x squared. Of course, when that happens, that just becomes 0. And I also have an opposite. What other color can I use? Purple, I guess. I think I just used purple right above it. I'll use brown, I guess. So then I also have a positive. Oh, I did it again. Darn it. I also have a positive 9x and a negative 9x. And of course, when that happens, that just becomes 0. That was 0 also. And so what do we have left? The only thing we have left is x squared minus 27, which is exactly what I had up here, right? Okay, so we checked it. Okay, so it is a bit of a mess. It's not very intuitive, but the formula works like a charm, and it's really the only way we can break those perfect difference in sum of two perfect cubes down. So you gotta get the procedure down to deal with those types of problems. They don't come up that often, but they do come up. So let's deal with the next one. This next one's starting off. We can see it is, can we write that as a perfect cube plus a perfect cube? The answer is yes, I can. Z times z times z is z cubed. And 3 times 3 times 3 is 27. So now what we have to do, so I have more trouble actually just trying to use my color on this darn thing. And so we're going to have z plus 3 z plus 3. We started with a plus. I think I'm going to go ahead and just show the signs. Then it's going to be minus. Then it's going to be plus. Don't forget that this term gets squared and this term gets squared. Okay, so now we have my first term gets squared, so z squared. And then I have a times b, so it's going to be z times 3. And then I get my last term squared, 3 squared. Of course, taking care of the squaring and everything, we have z plus 3 times the quantity z squared minus 3z plus 9. And there it is factored. And once again, if you multiplied that out, this is number 13, if you multiplied it out, you would get back to z cubed plus 27. We got z plus 3 times the quantity z squared minus 3z plus 9. Good. Okay, so now what about this mess of a problem? This is number 14. And I'm seeing perfect cube and perfect cube, but 81 is not a perfect cube. 81 is a perfect square, right? 9 times 9. Or it's a perfect fourth power, 3 times 3 times 3 times 3. But it's not a perfect cube. So it's not a difference of two perfect cubes, but they're telling us it's a difference of two perfect cubes. So what's going on here? What's the first thing you should always do when you're factoring anything, but, you know, highlight it with the binomial, because that's a binomial. What's the first thing you should do? Factor out the greatest common factor if there is one, and then go down your checklist to see if it fits one of those guys. And if you factor out the greatest common factor, or there's nothing to factor out, and you've checked the 3 binomials, then it's prime. You're done. But the first thing is to factor out the greatest common factor. And I'm seeing that there is, on number 14, a common factor of 3. So we're going to take that guy and we're going to factor out a 3. When I factor out a 3, I get 27x cubed. Ooh, 27 sounding promising. Minus, I factor out a 3, so divide that by 3, and I get 125y cubed. And that's looking promising. So let's try to identify, is this in fact a perfect cube minus a perfect cube? So let's use our color. 3x times 3x times 3x is 27x cubed. Perfect cube. 125y cubed. Well, that's actually 5y times 5y times 5y is 125y cubed. We don't have to worry about the sign. I mean, the sign is part of the formula, so it's a difference here. And then with that sign comes the rest of the formula, right? And so the rest of the formula is just going to be, can we do it? Let's take a second to, let me show an extra step. When you've done this quite a bit, you'll start automatically squaring the parts that need to be squared. But I think I need to take, this is only our third one, and this one's more complicated. So let's take our time here. So remember, it's going to be, sign is minus, so it's going to be a minus b times the quantity a squared plus ab, and then last one's always plus b squared. This piece is going to be squared, and this piece has to be squared. Okay, let's fit in the different parts we have. So this is our a, which is 3x. And it's going to be minus our b, which is 5y. And then we're going to have our a, which is 3x. And that gets squared. So, you know, if you did this step in your head, you would have written 9x squared. Be careful, because sometimes people forget to square the 3. That's a common mistake, so be careful on that. So now we've got our finished 3x minus 5y. Okay, next, a times b, so it's going to be 3x times the b value, which is 5y. So 3x times 5y is going to be 15xy. And we're almost there. Finally, we take our b value, which is 5y, and square it. 5y times 5y is 25y squared. And I think we got it. And that was not going to be done without a formula. We got 3 times the quantity 3x minus 5y times the quantity 9x squared plus 15xy plus 25y squared. My stomach is growling. I'm a bit hungry. I never know if you can hear that or not. A little bit embarrassing. Oh, wait, let's fix that y because I just made it worse. Oh, and I got rid of y squared. There we go. Number 15. Factor the following polynomial. They're not giving us any clue if it's anything special. Well, it is a trinomial. And I don't see a perfect square there. It's not going to be anything special, right? So let's see. Factor out the greatest common factor. We should always do if there is one. And if there's a negative in front like that, we like to factor out -1 even. Is there more than just -1? Yeah, I think there's at least going to be -2 that I can factor out. Let's start with that. See if we can factor out a -2 and see what happens here. On this particular problem, -2. Wait, is there anything else? Yeah, there's a y there, there's a y there, and there's a y there. Scratch that idea. Let's factor out -2y. What's left? Now remember, factoring out -2y is like dividing -2y by each term. And I'm going to show that because when you're factoring out a negative, it's very easy to make a mistake. So one way to help ourselves is to be thinking like you're dividing out -2y. And you really should just kind of keep that in your head. But when you're factoring out -2y, a negative over negative makes that a positive. So this is just going to be 10x squared. And once again, you could always test this by multiplying. -2y times 10x squared is -20x squared y. That's exactly what I started with up here, -20x squared y. So if that happens, you factored it correctly. Okay, so you could always kind of do little checks as you're going. The next is going to be a positive 18 divided by -2. So this is going to be minus, what's that, 9x. The y's canceled, so 9x. And finally, 14 divided by -2 is -7, and the y's cancel. So once again, you could actually multiply that out just to double check yourself and make sure that it still equals the thing you started with, right? So this problem, I hope you realize that by factoring out the -2y, this nastier problem right here turned into, not easy because it has that 10 in front, but definitely easier than the thing you started with. So let's see, let me zoom out a little bit and see how much space I have. What we're going to do here is we're going to get some color like we did before. What's the procedure? We multiply 10 times -7. And that gives me my product of -70. I'm trying to multiply to -70 and add to -9. So I'm looking and looking and looking. Well, if you don't find it, you better do something. Well, let's start with our signs. If I'm multiplying to a negative, then one of them has to be negative, one has to be positive. So let's just see what multiplies to 70. 1 times 70, nope. 2 times what, 35? Nope. 3, 4, how about 5 times 14? That sounded pretty good, didn't it? Because the difference of those is 9. So if I make the 14 the negative, so -14 plus 5 gives me -9, and -14 times 5 is -70. So we just found our two awesome target numbers. Forgot what color I used for that. I'm going to use green here. So remember our factoring by grouping technique just says replace that with our two target numbers. And so we're going to replace this green with the green over here, which is -14x plus 5x. And then copy the rest down, which happen to be 10x squared minus 7. Okay, now remember factoring by grouping. So we go through this whole grouping thing. What's common? Factor out what? A 2x. What is left? If I factor out a 2x, I get 5x minus 7. I get a 5x minus 7. And just to let you know, if you put the 5x first and the negative 14x second, you'll get the same answer. It's just you go along a different path. You get the same answer, but it's just a little bit of a different path to get there. Okay, continue on. Now we factored out and we're left with a 5x minus 7. We have to have a 5x minus 7 for this procedure called factoring by grouping to work. Have to have that. So I'm going to put it down and I'm going to see what can I factor out on this next group of 2 binomial to get 5x minus 7. Well, it's the same, so that means I'm factoring out a 1, right? 1 times that will keep it the same. So now you can see, what do I have left? Well, I have my common factors, which will factor out 5x minus 7. What's left from that is the black terms, which is 2x plus 1. And don't forget to carry down this negative 2y that we factored out at the very beginning. And so that somewhat tough problem, not too bad when we take our steps, is going to be negative 2y times the quantity, times the quantity 5x minus 7 times the quantity 2x plus 1. Cool. Okay, next problem, number 16. We're getting there. Things take a little bit of time. Number 16, especially when trying to explain. We got a binomial. So remember binomials. See, right, 2 terms, right? 1 term, 2 term, binomial. Remember, how do we deal with binomials? Factor out the greatest common factor if you can. Take a look at our checklist. Okay, that's it. So let's do it. Is there a common factor on number 16? And I think 7 is common. And I also see an a to the first and an a to the fourth. So that means a is common. So I'm going to factor out a common 7a. So think about it kind of in your head like dividing 7a. So that's going to give me 9b squared plus 49 divided by 7 is 7. A to the fourth divided by a is a to the third. Okay, whoops. And now at this stage, what we've done in the past, we're looking at the binomial, right? What step are we on? Let's see if I can get there faster. What step are we on? We're on this step now. Is my binomial one of these formulas? Is it? I got a perfect square plus a perfect cube. That's definitely not one of my formulas. This is done. It's already factored. The best we could do is factor out a greatest common factor. Number 17, we're getting there. Only 2 more problems. Ay, but look at that nasty problem. Okay, next little gem. And this is just a recommendation. But when you have 4 terms, you should try to factor by grouping. Which is a little bit different than the factoring by grouping with trinomials. Because the factor by grouping by trinomials, we have a trinomial, 3 terms, and then we use our little diamond process to find those 2 target numbers, split the middle term into 2 more terms, and then we have 4 terms. Well, we already have 4 terms here. So that's why we start right at this process with 4 terms, okay? So let's start with the 4 terms. Now, always, 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 I don't care if there's 2 terms, 3 terms, or 4 terms, factor out the greatest common factor if possible. And these are all even numbers, so at least 2 will go into it. Let's start with that. 2 will at least go into it. So if I factor out a 2, I end up getting what? If Factor out of 2, I get 9x cubed plus 5x squared minus 144x, right? I'm right there. And then finally, if I factor out a 2 there, I get a minus 80. So the next little piece here, what I want to do, let me go like that so I have a little more space to operate. And then I zoom in. The next thing I want to do now is factor by grouping. I got 4 terms, factor by grouping. What can I factor out there? Looks like I've got a common x. I think that's it. That's kind of a bummer, huh? So if I factor out an x, I'm left with 9x. Whoops, I'm sorry, we factored out x squared, couldn't we? Let me go back. So if I factor out an x squared, I get 9x plus 5. Now, on the next 2, I've got to match that 9x plus 5. Can I factor something out to make that happen? So basically, what times 9x gives me a negative 144x? Is that even possible? And anybody coming up with anything? Well, what we could do is just grab a calculator, right? Grab a calculator and 144 divided by 9. Oh, 16, there we go. So negative 16 times 9x gives me a negative 144x. And double check, negative 16 times 5 gives me a negative 80. Perfect. Okay, we got this thing taken care of. We got all the little pieces and parts. We know we first factored out a greatest common factor, which was 2. We know we're now going to have a, oh, darn it. We know we're now going to have common factor that factors out, which is this red 9x plus 5. And we now have the leftover stuff, which is just x squared minus 16. Okay, now you might feel like doing a victory dance, happy dance, whatever, because you're done. But whoops, this is one of those problems that kind of keeps on going. You have to make sure, is this prime? Yes, it's prime. Is this prime? Yes, it's prime. Is this prime? No, this is not prime. Because why? Because it's a perfect square minus another perfect square. That will factor down also. So it's not factored completely. Okay, let's finish it off. 2 times the 9x plus 5 quantity, and then factor that difference to perfect squares. Well, it's just going to be x plus 4 times x minus 4. Believe me, oops, and how did I write it 2 when I said 4? Believe me, that gets missed and forgotten so many times. Happens all the time. But that can go one step further to be factored completely. In other words, that x squared minus 16 is not prime. It's like if someone said in arithmetic and they told you to factor completely 12, and you said, yeah, okay, how about 3 times 4? And you said that equals 12, but they said, but you didn't do it completely because 4 factors down more to 2 times 2. It's the same kind of thing, right? Other than we don't have a perfect square, but it's the same kind of thing. You got to factor completely until you got yourself down to prime polynomials, right? Binomials or whatever they are, polynomials, okay? All right, and we're down to one nasty, nasty problem. Now this last one, I'll admit, is a pretty nasty problem, and I wouldn't ask this one on the test, but I just wanted you to see something like this. So the people that are going on to pre-calc and trig and all that will have at least seen it once, you know, and it's a tricky one that if you know, a lot of people would miss this, so don't feel bad. I think even bringing it to, I remember students sometimes bringing it to tutors in the math lab, the tutors kind of scratch their head because you see 4 terms and the thing you should be trying to do is factor by grouping, which is the right instinct. Well, the first thing is factor out the greatest common factor, and there isn't any. The second is factor by grouping, and that doesn't work, so you're getting frustrated. But really what's happening here is there's a pattern that's hard to see. I'm going to write out what we have here. We have 36 minus a squared minus 8ab minus 16. And I would say pretty much no one gets this right until they do it a couple times. And then they have to remember it in the future, right? So it's one of those things, it's just tricky. So what we're going to do is we're going to rewrite this. We're seeing that this might have potential to be a perfect square. And this definitely is a perfect square. So if I could write this as a difference of two perfect squares, I would have something. So let's first write that 36 minus, there's my difference, of this stuff. Well, when you factor out a minus of the whole thing, I mean, this little symbol is only going to a squared. And we want it to be minus the whole perfect squared. So basically, we're going to have to factor out a negative or a -1 if you want. So it's just going to basically change all these signs. And you can verify that if you distribute your negative, it should get us back to -a squared, -ab, -16b squared, and it does. So, okay, now that's the first and hardest step probably, because now after that it starts to make sense. That is definitely the killer step. Once you see that, you have a chance. Is this a perfect square? And you're going to say, yes, it is. Before I go to this, let me do this over here. Is this a perfect square? So remember how we check that. If it's a perfect square, whoops, it always does that to me. If it's a perfect square, then we have the first term has to be a perfect square, and the last term has to be a perfect square, and the middle has to be 2 times a times b. Remember all these that we did at the beginning? That's what we're doing right now, except it's incorporated in another problem. So, is that a perfect square? Yes. A times a is a squared. Is this a perfect square? Yeah. 4b times 4b is 16b squared. Here's the kicker. Is the middle, is the middle 2 times the a value, which is that a, times the b value, which is 4b. And that's what we have to check to verify that this is a perfect square. So 2 times a times 4b is 8ab, and that's exactly what we have in the middle term. So that is definitely a perfect square. Let me write it as a perfect square now. That is definitely a perfect square, and so this is a, and then the b value, 4b, and then the sign. What was the sign? Oh, the sign was plus. And then let's take a look at this side. Is that a perfect square? That's the easy one, right? That's just what, 6 squared makes a perfect square. 6 squared makes 36, so we're good. So now all we have to do, we're running out of space, all we have to do is now write our difference of 2 squares. That would be, dang, I'm definitely going to run out of space here. That would be, I shouldn't have gotten so aggressive with my writing. That would be, remember, the difference of 2 perfect squares. It's going to be the a plus the b, right, times the a value minus the b value. And our a's and b's are, the a is not too bad, right? 6 plus the b value. And when I say b value, I'm not talking about these red and blues. I think I'm going to stick with one color at this point. I'm just talking about in the formula, that second one's called a b value. The first one's called the a value. So it's going to be 6, the first, plus the second, which is just this guy right here, which was, I guess I have to use the color now that I've started that. That's just going to be a plus the b. Okay, and I would recommend keeping that in a parenthesis. Of course, when you're adding, it doesn't matter if you have the parenthesis or not, but when you're subtracting, it really does make a difference. So let's do the next one. Remember, our value was 6, and then our next value happened to be that red A, and that blue 4B. So I just copied that, right? That gets put right here and that gets put right there. Okay. So we are almost done. I would say the only last little bit, the last little problem here is, I'm not sure, I didn't check if they would let you keep it like this, but usually you want to simplify it. So that's just going to be 6 plus a plus 4b. And this is 6 minus, now distribute your negative, minus a, distribute your negative, minus 4b. And that's how I put it in, that's normally how we like to see it. That's how I put it in MyLab, and that was correct. Don't know if they'll be lenient on that one, so you probably should just distribute the negative, and away you go. All right, that was a workout, and here we are. Let me clean that A up a little bit. It's bugging me for some reason. I'm sloppy everywhere else, and then every once in a while, one tiny little tail of an A bugs me, but I don't know. I hope that helped out, and I hope you're having a great day, and take care, and talk to you soon. Bye.